So let's consider what a scattering matrix for a three-port device that's matched, lossless, and reciprocal, what that would look like. And so it's interesting. I think this is one of the most interesting thing of scattering matrix theory, and the idea that you can impose mathematically restrictions on the scattering matrix that map from physical descriptions of the device itself. And so this one is very interesting. If we go through and we start with the fact that the three-port device is reciprocal, and again, it's hard to mess up reciprocity, so almost certainly that's going to be true, then the scattering matrix must be symmetric, and we come to the first of three equations. S21 is equal to S12, and likewise for S31 and 13 and 23 and 32. Additionally, if the device is matched, and again, this is something that is very desirous if we have a device that works in a microwave network or a microwave system, then we want it to be a matched device. And from that standpoint, then the elements of the scattering matrix, the diagonal elements, must all be 0 if they are matched. And so if we have a three-port device, here's a picture of a three-port device. These are SMA ports, the SMA connectors for SMA transmission lines, a microwave device here. If it's matched, the diagonal elements are 0. If it's reciprocal, which it almost certainly will be, then the elements are symmetric, and this is true. What do we have? We have all of a sudden 1, 2, 3, 4, 5, 6 equations already with respect that constrain what the scattering matrix might be. So we have 6 equations, but of course we only have 9 scattering parameters in our 3x3 matrix here. And when we constrain our scattering matrix such that it satisfies those 6 equations, we're left with the scattering matrix that looks like this. And we see that there is just 3 scattering parameters, non-defined scattering parameters in this entire matrix. Once I know S21, 31, and 32, then we know the entire matrix for this three-port device, which is reciprocal and matched. So as we add equations, we start to really constrain what the scattering matrix might look like. So let's constrain it even further. Let's say that our three-port device, in addition to being reciprocal and matched, must likewise be lossless. In other words, the scattering matrix, the 3x3 scattering matrix, must be unitary. Its 3 columns must form an orthonormal set. And so from the standpoint, the definition of normality, we find that the 3 equations must be satisfied here. Here's the magnitude of the first column vector, the second, and the third. And of course, we only have 2 terms because one of those column elements is 0 because of the matched nature. All the diagonal elements are equal to 0. So this must be true. Likewise, if we go through and apply the idea that the 3 columns must be mutually orthogonal to each other, and we take the complex conjugate dot product between the two, we find we get these 3 equations. This is between column 1 and column 2, column 2 and column 3, and column 1 and column 3, I believe is how that works out. Now, if we look at this, it says this complex number is equal to 0. And this is important when we write something of this form. This is a complex 0. In other words, its real part is equal to 0 and imaginary part is equal to 0. When we say a complex number is equal to 0, we say that both its real and imaginary part must be equal to 0. So these are 3 real equations, and these are 3 complex equations, which can be separated into 6 real equations. The real part of this must be equal to 0. The imaginary part of this must be equal to 0, and so forth. And so we can look at this and see that we have 9 real-valued equations that must be satisfied with just 3 complex unknowns. And so we've over-constrained ourselves. Every complex value has, of course, a real and imaginary part, if you want to look at it that way. And so we have 6 real values to satisfy 9 real equations. And so it turns out that's it's over-constrained. It turns out there are no solutions then to these 6 equations. You can kind of see this if we, instead of talking about a real and imaginary, let's take the magnitude of these 3 equations. If the magnitude of if this is 0, then the magnitude of this is equal to 0, which means the product of the magnitude of S31 and the magnitude of S32 is equal to 0. Well, that means that one of those 2 magnitudes must be equal to 0. The same thing here. One of the 2 magnitudes must be equal to 0, and then the same thing here. We could satisfy all three of these if, let's say, the magnitude of S31 was equal to 0 and the magnitude of S32 is equal to 0. This equation certainly be satisfied. This would be satisfied because the magnitude of S32 is equal to 0. This equation would be satisfied because the magnitude of S31 is equal to 0. But if the magnitude of S32 and S31 were equal to 0, then it would not satisfy this equation. The magnitude squared of S31 plus the magnitude squared of S32 is equal to 1. We found that the only way that we could satisfy this, or one way to satisfy this, would be if two of them magnitudes were equal to 0. Let's say this one and this one. But if that's the case, then obviously their sum is going to be equal to 0 and not equal to 1. So hopefully I'm just trying to show there is no solution for these equations, no set of complex values S31, S32, S21 that will satisfy these equations. Now, this is just a mathematical statement. We've gone through and we've defined these sets of equations, essentially 6 real-valued equations there. And again, mathematically, we can show that there's no answer. But remember, these mathematical statements are representations of a physical artifact. The fact that it's matched, the fact that it's reciprocal, the fact that it's lossless. Because there is no solution, that means that there is no 3 by 3 matrix that has zero value diagonal elements that's reciprocal, or symmetric, I should say, and likewise is unitary. There's no such thing as a 3 by 3 unitary symmetric matrix with zero value diagonal elements. And because of that, there is no such thing as a 3-port microwave device that is matched and lossless and reciprocal. So it turns out we could build a microwave component, a 3-port microwave component that is matched and reciprocal. We can build a 3-port microwave component that's matched and lossless. We can build a 3-port microwave component that is lossless and reciprocal, but we cannot build a 3-port microwave component that is both, or simultaneously, all three things, matched, lossless, and reciprocal. Because if we could build one, it would have a scattering matrix, and that scattering matrix would be symmetric, unitary, with zero value diagonal elements, and no such 3 by 3 matrix exists mathematically. So I think this is kind of fascinating that we can prove that nothing like this exists by mathematical means, given that we understand the physical ramification of the mathematical artifacts of our scattering matrix. Oftentimes students have a hard time buying this. They think surely there must be some device that would be all three of these things. They make the argument that we can't prove a negative, so you can't say that there is no such thing. But in this case, we can prove a negative. We can show it mathematically that there is no such thing as a matched, lossless, reciprocal 3-port device. Now, it turns out there is a matched, lossless, reciprocal 2-port device. That is possible, meaning that there's a 2 by 2 matrix that has zero value diagonal elements, is symmetric, and is likewise orthonormal. We'll see in a second what happens with a 4-port device, whether we can make a matched, lossless, reciprocal 4-port device. That's the topic of the next presentation. I will add, though, that we can build a matched reciprocal device that's almost lossless rather. It's lossy in a strict sense, but if we sort of ignore a couple of ports, then we can make a device that looks like it is lossless in addition to matched and reciprocal, even though it is not strictly the case, and therefore does not have a unitary scattering matrix.